I have two more stories, and I'll see if I can get through them relatively quickly. So this one has to do with a failed supernova. It's been long thought that black holes, or at least stellar-sized black holes that are tens of solar masses in size, they originate from supermassive stars that blow up in supernova. But there's been observational evidence to suggest that not all black holes go through end up as, not all stars that end up as black holes actually go through a supernova stage. And so the authors in this work, they have been looking at galaxies with the Large Binocular Telescope to try and find supernova, and they're trying to find evidence for these so-called failed supernova that led to black holes but didn't actually blow up. And so what they did was they used the Large Binocular Telescope, a telescope that's also in southern Arizona, and they they monitored 27 galaxies over a period of 7 years. And what over this time, I mean, it's very hard to predict when a galaxy might have a supernova occur. But if you watch enough galaxies for a long enough period of time, chances are you might be able to find a supernova. So here are some supernova that they discovered. The pictures are kind of odd looking. So these initial images are black just because it's easier for the human eye to detect black on white than white on black. So these are kind of inverted images. And but what happens is that staring at the star in 2008, 2012, and then these whiter images, because of the processing that they do, are when the star has suddenly grown brighter. So this is when it's going through the supernova stage, and then it starts to decrease. And then when it is black again, it's basically dimmer than when it started. So you can see that over this period of monitoring from 2008 to 2016, they were able to find, or at least detect, this one particular supernova in this one galaxy. And then here are the other ones that they found in the survey. And so that's not a whole bunch of supernova that was detected, but that's still pretty good for 27 galaxies over a period of 7 years. So I think they found 1, 2, 3, 4, 5 supernova. Well, in the sixth possible supernova was this particular star, N6946BH1. And so here it is in 2007, observed with the Hubble Space Telescope. And then it was observed again in 2015. And you see that there's nothing there. And here is what's known as a light curve, meaning we're plotting over time, so you can see the years from 2000 all the way to 2016, and they're able to find some data from previous Hubble Space Telescope observations before the start of their survey. That's what these points are, and the different lines represent different colors. In blue, visible, which is close to green, red, and this is kind of a near-infrared band. This F10, 110, and F160 are also in the near-infrared that were observed by Hubble. And then they also looked at the star with the Spitzer Space Telescope, which observes in the mid-infrared, which is even further in the infrared. So what they were able to find with all these different observations from many different telescopes is that right around 2009, the star jumped up in brightness. So it went from about 10,000, or actually 100,000, that's 10 to the 5, solar luminosities, meaning 100,000 times brighter than our sun. That was kind of the normal brightness for the star. And it jumped up to 10 to the 6, which is about 1 million times. So, that seems like, wow, that's pretty bright, but that's no supernova, because supernova can be billions of times brighter than our sun. And so over a period of several months, it was pretty bright, and then it dropped again. And in some wavelengths, like this green, which is invisible light, it's almost practically zero. I mean, it's pretty noisy, but the star has almost completely disappeared. There's still some starlight in some of the other bands, but the far infrared or the mid-infrared is the only light that is still coming from this particular star. So the authors go through all the different possibilities for what might have happened, and they basically discounted, based on the observations, any other type of scenario. And what they think happened is that the collapse that resulted in the black hole managed to create a shock that blew out the outer envelope of this red supergiant star. And so the brightness that they saw that increased in the star in 2009 was a result of this outer envelope being blown off. And then over time, as this envelope increased in size, the brightness fell off, but this outer envelope created a lot of dust, and this dust would emit infrared radiation. And so the reason why we're able to see sort of this constant mid-infrared is from that expanding dust from the star.